Well, we've gone through finding the area with rectangles manually. We developed the Riemann sum. We used the Riemann sum for a larger and larger number of rectangles and finally came up with the idea that what we were looking at was a limit. So, limit of what though? Well, the thing that we're taking the limit of is our approximate area which is found using this Riemann sum. Of course, the more rectangles we used, the better our estimate is getting until, in theory, if we could go forever, we should eventually get the exact area. So what we are looking for here is the limit as n goes to infinity of the Riemann sum. All right. That's going to be the exact area. Now the good news is it starts with the same Riemann sum that we've just spent the last, hours worth of videos establishing. We're only going to throw one other step at the end of it. But, as you'll see, it actually turns out very nicely. Evaluating that limit is not going to be a problem. The trickiest part of this is going to be that in order to have n approach infinity, we can't actually put in a value for n. We have to leave it as n so that eventually we can get to the limit and let the limit do its thing. So that's going to be the toughest part of this, is we're going to have to leave n alone. But perhaps that's not that horrible of a thing, because what we saw going through all those repeated calculations with n is 8, n is 100, n is 1,000, n is 100,000, was that changing value of n was basically the only part of the entire Riemann sum formula that changed. So maybe it's not going to be that horrible. Well, let's try it out. We've got the function f of x equals x squared on the interval from 0 to 2. Delta x is still going to be the total width of the interval divided by the number of rectangles. But this time, we're going to leave the number of rectangles as n. Now perhaps you can see why I never bothered simplifying the delta x fraction. Because this can't be simplified without knowing what n is. We were fortunate that the width of the interval was an even number of 2, and that the number of rectangles we were using was always an even number and therefore could be simplified. I chose not to, and as a result what you'll see is a lot of similarities here to what we did when we actually had a specific value of n. So I did that on purpose. Now, x sub I is a, which is 0, plus 2 over n times I. The 0, of course, since we're adding 0, that does nothing, so it drops off and we get 2 over ni. One more step, f of x sub I, where we take the expression for x sub I and use it as the input expression to the function. Here's again where you're going to get to see some of those similarities. 2 squared is 4. Now, I can't square n without knowing what it is, but I can write n squared, which should seem familiar, because even when I did know what n was, I still wrote it as that number squared. And of course, I squared. All right, onward to the Riemann sum. Now, we're going to keep that stuff up here. Now, the exact area is the limit as n goes to infinity of the Riemann sum, where f of x sub I is 4 over n squared I squared times delta x. And again, you should see some very familiar bits of this. Now, we're going to, of course, start with what's inside the brackets. So we're going to start with all the stuff we did before, simplifying the summation. At this point in time, the limit as n approaches infinity is simply along for the ride. We will get to it later. So, for now, we can do what we did in the previous times through this. We can take the 2 over n times the 4 over n squared. Because remember, n is a constant in terms of the summation. In the summation, I is the variable. N is a constant, which usually we know, in this case, we're leaving it as an unspecified constant, but in terms of the summation, n is a constant, which means 4 over n squared is a constant, 2 over n is a constant, and they can be multiplied together. 4 times 2 in the top is 8, and in the bottom, n squared times a third n is n cubed. So again, a lot of really familiar aspects of this. Well, 8 over n cubed can go in front of the summation, not in front of the limit. We're not up to the limit yet, but it can go in front of the summation. Now, at this point, when we knew a value of n, we turned to the summation formula for I squared. Of course, we can't put in values if we don't have them, but we can still write the formula. In fact, the formula originally is written in terms of n anyway. So let's take this and move it up here. So we have the limit as n approaches infinity of 8 over n cubed times the formula for I squared with an unspecified value of n. Okay, so this one we're not going to be able to put into our calculator. But we don't have to. We can do some little things at least, like we can still do that same cross-simplifying that we had every other time where we actually knew the value of n. We can still do it. That's kind of the cool thing, is algebraically, all the steps we've taken so far are identical to everything we did when we knew the value of n. We just happen to not know it. But algebraically, everything else is identical up till this point. Now, we can do a little bit to clean that up, which would probably be a good idea because we're about to do a limit. So if we can get this as clean as we can, it'll make handling the limit easier. So what we can do is FOIL out the numerator. So n plus 1 times 2n plus 1. At this point, we should be able to FOIL out pretty well, so I'm not going to take the time to go through those steps. We can then distribute the 8 into that as well. But actually, we have a very fortunate thing here. The denominator is monomial. We can also distribute the denominator. So the 8 goes into this, and that becomes 16n squared, but the denominator is also going to distribute to it. The 8 is going to distribute to the 3n and make that 24n, but the denominator is also going to distribute to it. And the 8 will distribute to the 1. But the 6n squared will also distribute in the denominator. Well, in this fraction, the n squareds cancel out entirely, and the 16 over 6 reduces to 8 over 3. There's a familiar value. In this case, there's only one factor of n in the top, which means only one factor will cancel out of the bottom. Now, because of that, I'm not even going to bother with the 24 and the 6, because they're incidental. As n goes to infinity, if the numerator is constant, the bottom will grow and grow and grow, and this whole fraction is going to approach 0. So it doesn't really matter what those things are. What matters is that the bottom will grow while the top remains constant. This one, again, the 8 and the 6 could be simplified, I suppose, but what's important about it is that we have a power of n in the denominator, and that's going to approach 0. So this term here will approach 0, and this term here will approach 0. But this term is a constant. There's no n in it. So it's completely unaffected by n going to infinity. The limit of a constant is that constant. And that is exactly the value that we saw in our numerical approach, or the value that we supposed we were going towards. But now we can get there and get the exact answer, and we can do it in one shot, which is huge. It saves a boatload of time, because remember, we had to go through this calculation with only minor changes each time, but we had to go through this calculation all the way up to here, at which point we used our calculator, and we had to do it with slight alterations for new values of n, but we had to do it over and over and over and over again. Numerical limits are solid. They will always get you there, but sometimes they take an awful lot of work and an awful lot of time to get there. Algebraic approaches, however, by just sticking that limit on the front and being able to evaluate that limit, we can get the exact area of a region that easily and that quickly. Now, there is one more video where we're going to look at a different function on a different interval, because I don't want you thinking that every single problem is going to look the same just because every single one of these has looked the same. The reason they've all looked so similar is because it's the same function on the same interval through every single one of these we've worked through. If we change the function, if we change the interval, we change the result, and we change what everything's going to look like. So, one more example of this to conclude this lesson.